spelling here, just in case. So today we will talk about non-holonomic systems. And first we'll start with non-holonomic, or sometimes we call them Pfaffian constraints mechanics. So there are constraints on the following form. So this is like the ith constraint, which is function of q's and q dots, generalized coordinates and velocities. They are linear in velocities. So j1 to m aij of q times qj dots. So they are linear in velocities. We have seen them in 241. Our dynamics course. So this is, here's an example. This is x and y. This is like a trajectory for this rolling disk, and it's rolling without slipping. So here is the x and y coordinates of the center, and it rotates with an angle theta. So this is like the r, the radius r. So this velocity vector, the tangent to the trajectory is r theta dot, is making an angle phi with the x-axis, and you can write down the no-slip constraint as the relative speed, the relative velocity here is 0, right? At the contact point, and because the floor is just stationary, the velocity here is 0. Now we have two contributions coming from x and y of the center plus r theta dot. So x dot, in the opposite direction we have r theta dot cosine phi, this is 0. Also y dot, we have r theta dot sine phi, this is 0. Any question about these two constraints? Inducing no slip, rolling without slipping, relative velocity when the floor is 0. If you have a question, feel free, please. Don't feel shy or anything. So this means that if I have four generalized coordinates, x, y for the center, theta, and phi, this is one representation. If I have four generalized coordinates, my velocities are constrained by these two equations. So I have only two free velocities. So if you have only two free velocities, a legitimate question was, okay, can you reach any given configuration, x, y, r, and theta? This is a very legitimate question, right? And you answer that via checking the integrability of these constraints. We already did that before. I'm doing a quick review. I'll not do the integrability again, but what I want to stress is that I can write these two non-holonomic constraints as a control system, because I have four velocities in general, x, y, theta, and phi, and I have only two free velocities, and everything is linear in velocities, so it's something times theta dot plus something times phi dot. So only two free velocities, say if you choose to represent them by theta dot and phi dot. Okay? So you can write the entire thing in terms of theta dot and phi dot, and you can simply fill in these. So x dot is r cosine phi times theta dot, 0 over there. Same here, r sine phi and 0 over there. Theta dot is simply 1 times theta dot and 0 here. And phi dot is the other way around. So if theta dot and phi dot are free, say these are your control inputs, you can assign them freely. I can write down this system as follows. X dot, where x now is an array representing all the configuration coordinates, equals, this is your g1 of x times u1, this is your g2 of x times u2. Okay? So given a set of non-holonomic constraints in mechanics, we can write them as a control system. In particular, it's driftless. There is no drift. Okay, any question about that? So only two free velocities, so you have two controls, and we ask, can we reach all these four states? This is an integrability question. You use Frobenius theorem multiple times or you check the log. We did that before, but what I want to stress is that given two constraints, they are non-holonomic constraints coming from mechanics, I can write down an associated driftless control system. So indeed, non-holonomic or Pfaffian constraints, so linear in velocities. These arise from non-holonomic constraints like rolling without slipping or conservation of momentum. If you have a conservation of momentum equation, it will be also linear in velocity, because by definition momentum is linear in velocity. So you can write them as an equation in this form and turn the system into a control system. So non-holonomic or Pfaffian constraint is exactly equivalent to what we call driftless. There is no drift. Okay? Driftless, sometimes we call them kinematic systems, kinematic control systems, because they simply represent kinematic equations. There is no dynamics here, right? If you assume that you have direct control authority over the speeds, and you're asking the following question: how can I manipulate my speed to reach any final configuration x, y, theta, and phi? This is a very legitimate question. Roboticists are always interested in that, right? Given the speeds, how can we manipulate the speed to reach the desired position? So hence the name actually in the control community, they call this non-holonomic systems. So non-holonomic systems, this is the, so it's x dot equals summation j equals 1 to n gj of x. To us, they are just driftless systems. In the control community, you will hear the word a lot, non-holonomic systems. It's because they mainly come from non-holonomic constraints. Okay? And of course, they should be satisfying the log. Why? Because the log in this case is necessary and sufficient. If they don't satisfy the log, the algebraic rank condition, then the system actually will live on an integral submanifold. They will not reach the entire space. We don't need to study them. Please go and add one more actuator to at least achieve the log. So this problem is very common in the sense, this set of equation is very common. If you write down the kinematics of any mechanical system, assuming direct control authority over the speeds, and this is your positions, then it will be written on this form. So any mechanical control system, the kinematics will be written on this form. Okay? If you have no constraints whatsoever, then M will equal N. But if you have some non-holonomic constraints, you don't have freedom over all the speeds, then M will be less than N. Okay? Or if you have some conservation of momentum, then M will be less than N. And if M is less than N, which is the typical case, otherwise it's too luxurious to deal with. If M is less than N, then linear theory fails. All what we have from linear control theory will not work here. Simply the system is uncontrollable. If you check the controllability of this system, linearize around the origin. So obviously you're going to just restrict these guys at the origin. So you get M columns in your B matrix. And to have full ranks, there is no A matrix here. To have full rank, these B's should span the entire thing. So we should have N of these vectors. Okay? So whenever we have M vectors less than N of number of the states, the linear control theory will always tell you that the system is uncontrollable. And as a control engineer, what is the immediate consequence? Is to add an actuator, right? So I keep adding an actuator, and the issue is that the linear theory will not work unless you have number of actuators equal to the number of states, which is ridiculously stringent. So the linear theory will always fail here. We need to go to nonlinear systems, okay? This is our topic today, the non-holonomic systems. Any questions so far about that? Any questions? You guys need to come up with questions. I mean, this is a graduate course, and I always learn from graduate courses, undergraduate too.
Professor, in case of holonomic systems, is there any case holonomic system here? Like, is there any term?
Say it again. Is there
any holonomic systems?
holonomic constraints? You mean holonomic constraints?
Yeah, you said holonomic systems that comes from non-holonomic constraints.
Non-holonomic systems come from non-holonomic constraints. Oh, I see what you're saying. Yeah. No, because they're not interested. They're not interesting. Holonomic systems mean that you can live on some integral manifold, some manifold, right? So by definition, you cannot reach the entire state space. You just live on a slice. It's not interesting from a control perspective. Yeah.
And what are the cases where we have drifts?
Yeah, we will deal with it later, because this is much easier. And even though it's much easier, we'll see how challenging it is. So so here this is driftless control systems. Again, driftless, sometimes the community call them non-holonomic systems. So just to give you an idea about what is the source of challenge. Again, our paradise. Okay. So we have x dot equals ax plus bu. Okay. This system is controllable, right? If and only if what? Anybody remembers? For time varying A and B, we have a little bit generalized thing. You need to check the controllability gradient. So this is the integral from 0 to t, phi of tau, b of tau. So I'm allowing time variation of the A and B matrices here. B transpose, again phi transpose of tau d tau. So for a given t, the result is a matrix that depends on t. And if this guy is invertible for some t, then we're done. So it's if and only if, okay? Okay, so that's okay. What is the new here? The point is, controllability for linear systems is constructive. What do you mean by constructive? So first of all, what do you mean by controllability? By controllability we mean, well, there exists a control input history that gets you from x0 to x final, okay? When you prove that there exists, for linear system, it's not only existence, it's actually, here is the control system that will do it for you. It's a constructive proof. So it gets you the solution already. Here is the solution. U of t equals negative b transpose of time times phi. I guess this is transpose. You need to check this because it's complicated. This is t. W inverse. You just told me that W is invertible. As a consequence, if I can invert it, here is the control law that steers you from x0 to x final. This is phi of t final x final. Check this form after me. So this control law will steers x0 to x final in time t final, and actually minimizes j from 0 to t final, the control energy, the norm square dt. So this control input history. Here it is. Did you prove controllability? Here's the solution. Okay? For nonlinear systems, so we have x dot equals, say, f of x drift plus some terms gj, uj, and even if you assume driftless, we have an necessary sufficient condition for controllability like linear systems, luckily, which is the log, but it is not constructive. So having proved controllability, we still don't know yet how to steer from x0 to x final. The proof was not constructive. So the steering is a problem, is still a problem now, and this posed the following research problem over the 80s and 90s, which is called motion planning of non-holonomic systems over 80s and 90s. Okay? Any question about that? So let's get some idea about how we can do steering for non-holonomic systems. I'm getting these from a paper on non-holonomic integrators. It's a bunch of non-holonomic systems. Of course, the linear theory cannot tell anything about. So Brockett provided a bunch of these in his paper, 1981. Here is one example. So Q1 dot is U1, Q2 dot is U2, and Q3 dot is Q1, U2 minus Q2, U1. So in our lovely language, this is 1, 0, negative Q2, 0, 1, Q1. So this is your G1, this is your G2. Obviously, G1 provides motion along the first state directly, G2 does the same, and the Lie bracket between G1 and G2 is 0, 0, 2. So provides motion along the third direction. The third direction is driven by the Lie bracket between G1 and G2. Linear theory here will tell you that the system is uncontrollable. Okay? You cannot move along Q3. So before going and doing the motion planning, let's see what is the relation, what is the intrinsic relation between controllability and geometry? Why we're using differential geometry? Aside from the word differential, what is the relation between geometry and controllability in general? At least for this simple example. It's a little bit of a digression, but still related. Okay, I have complete control authority on Q1 and Q2, right? I can steer them the way I like. The issue is for Q3, right? So here is Q3 of final time, T final, is Q3 of 0 plus the integral from 0 to T final of Q dot, which is Q1 U2 minus Q2 U1. This is dt. And we know that this guy is Q2 dot and this guy is Q1 dot. And Q1 dot dt is simply dQ1. So this is Q3 0 plus integral of Q1 dQ2 minus Q2 dQ1. The integral now is not over time anymore, it's over the line. It's a line integral, right? So for example, if this is Q1, Q2 plane, this is your state space, right? But projected on the first two states.